طيب شكرا شباب. We talked last time about the table, steam table and refrigeration table, and how to use this table using any two independent and intensive properties. Actually, we can define either if it is steam, I will be using steam tables, or if it is refrigerant, I will be using actually the refrigerant table. We said last time also that we have another substance, which is the ideal gas, and we have applied actually the ideal gas equation of state, which state actually that BV is equal to RT. And we call this actually as the ideal gas equation of state. This equation actually is applied in case when we do have an ideal gas. But how we can actually define the ideal gas condition? Ideal gas actually is defined as a gas with very low pressure and high temperature. Or we have a gas actually with low density. We have a specific volume by definition. This specific volume is equal to 1 over density. So based on the ideal gas equation of state, the density will equal to, this is 1 over density, then we can take it actually to the other side. So the density will equal to pressure divided by R multiplied by the temperature T. So if we have a gas under very low density, that means actually this gas under low pressure or high temperature. Okay, so if we have a gas under low pressure, then its density will be low, or actually when we have a gas under high temperature, that means the density of the gas will be low in this case. And this is actually the pure condition to have actually a gas under ideal condition, or what we call actually the ideal gas in this case. Okay. But also the case is not clear how we can define a gas. Let's say we have a gas. This gas actually is existing at pressure B and temperature T. How we can define this gas actually as ideal gas or a real gas in this case? Actually, we can say ideal gas or real gas with respect to actually to the critical condition. Okay, so if this pressure value is close to the critical pressure, we have defined the saturation curve on the PV and TV diagram. This is the saturation curve, and we said the top point actually here is the critical point at which the pressure is P critical and temperature is T critical in this case. If the pressure value actually is close to the critical pressure, that means actually this gas under high pressure. But if the pressure value is low value, that means actually with respect to the critical pressure, that means actually this gas is under low pressure in this case. Okay. But if we have a gas actually under high pressure, then in this case actually we cannot use the ideal gas equation of state to calculate the properties of this gas, because in this case actually due to the high intermolecular force, in this case actually we'll have a big error in calculating the specific volume of this gas. Okay, and that's why we have to modify this equation using what's called actually the compressibility factor Z. So in this case we have to modify this equation using actually the compressibility factor, which we call actually the factor Z, to account actually for the actual volume of the gas. So in this case, instead of using actually the equation BV is equal to MRT, in this case the equation will be modified to BV multiplied by equal to Z. Z is the compressibility factor multiplied by R multiplied by the temperature T in this case. And this compressibility factor is defined actually as the ratio between the actual volume divided by the ideal volume of this gas. This compressibility factor Z, if it is equal to 1, so this is actually the case when we have an ideal gas. In this case, actually, if this parameter Z is equal to 1, then in this case, actually, we will get back to the normal ideal gas equation of state BV is equal to RT. So in case when this parameter Z is equal to 1, that means actually we have an ideal gas, because in some problem, inshallah, you will see, it may give you a gas at a given pressure and a given temperature, and they will ask you a question, is this gas actually representing a real gas or ideal gas? Then in this case, I will be just calculating the compressibility factor Z. We will learn how to calculate it. Then if this value is equal to 1, that means actually this case actually is the ideal gas. Otherwise, actually, if this value is greater than 1 or this value is less than 1, that means in this case we have a real gas behavior in this case. Okay, so if he gives you the pressure and temperature, I can calculate the compressibility factor Z. If it is equal to 1, this is the only case we can consider the gas as an ideal gas. Otherwise, actually, if it is greater than 1 or less than 1, this case actually will be the case of the real gas. Okay, this parameter Z from this equation, V actual over V ideal, or it is equal to actually BV divided by BV divided by RT in this case. Okay. طيب we said يا شباب an ideal gas. We said ideal gas at low pressure, if the gas actually is existing at low pressure and high temperature, then in this case the density will be low or the intermolecular force will be low, then we can apply the ideal gas equation, of a state. But if it is at high pressure, then in this case it is the real gas case. But high pressure or low pressure with respect to what? We said this is actually with respect to the critical condition in this case. That means this compressibility factor Z should be function of what? Should be function of the critical pressure, should be function also of the critical temperature, and should be function of the critical specific volume in this case. V critical in this equation, based on this equation, we have V critical is equal to B critical divided by, is equal to RT critical divided by the critical pressure, which is B critical. So this parameter compressibility factor Z should be function of the critical condition, the critical pressure of this substance, critical temperature, and the critical specific volume, which is RT, based on the ideal gas equation of state, will equal to RT critical divided by the V critical. But how we can calculate actually this compressibility factor Z as function of the critical condition? First of all, if you look at table A1 for any gas, he will list you actually the value of the gas constant R and the molecular weight, and he will give you also the value of B critical, T critical, and also the V critical, which is the critical specific volume. So look at this table A1, the first table in your table, and the tables here. Look at table A1. In this case, actually, you will find a list of all gases here, starting here, ammonia, argon, benzene, until actually we end up actually with water, and we have here actually another gas. So in this case, actually, if you look at any of those gases, you will find the chemical formula will be given, and in this case, the molecular weight will be given. The gas constant R, which we have defined R, the gas constant actually is the universal gas constant divided by the molecular weight of the substance. Then here, actually, in the last three columns, you will find the critical condition are given. Okay, pressure T critical, temperature T critical, B critical, which is the critical pressure in megapascal, and also the critical specific volume. This critical specific volume is equal to RT critical, the gas constant R, multiplied by T critical divided by the B critical. If you do so, then you can get actually the value of the critical specific volume in this case. Does that mean if we have a gas, let's say actually we have any gas at a given pressure, given temperature, and let's say given a specific volume. So in this case, to calculate the compressibility factor Z, we have to calculate actually the relative or reduce the value of those properties. So first of all, I can calculate the reduced temperature. T reduced will be the ratio between the given temperature divided by the critical temperature. And also the reduced pressure will equal to pressure, given pressure divided actually by the critical pressure. And also we can calculate the reduced specific volume, which is the specific volume divided by V divided by V critical, or V divided by V critical, which is RT critical divided by V critical in this case. Okay, and then actually they have done this for different gases and of different temperature, different specific volume, and they have calculated those actually reduce the values, reduced temperature, which is the temperature divided by the critical temperature, also the specific volume, and also the reduced pressure. And they came up actually with a generalized compressibility chart. This chart actually is a chart A15. So using any of those two parameters, any two actually of those three parameters, either reduce the pressure, reduce temperature, reduce the specific volume, any two of them, we can just take those and go to chart A15. Then from this chart actually we can calculate the compressibility factor Z in this case. If you look at this chart A15, okay, and I will look at it in your table right now. So this chart actually gives the value of the compressibility factor. This is actually the vertical axis, and the horizontal axis actually is the reduced pressure. And for different values actually of reduced temperature, each of those lines actually represent a value of the reduced temperature T reduced. Okay. And also in this chart, you will find the normal lines to the reduced temperature are representing the value of the reduced specific volume. So in this case, actually, if you are given here, let's say the reduced pressure is given with the reduced temperature. So with this reduced value of pressure, starting here actually from 0, this value actually is given up to a reduced pressure value equal to 7. Okay. And also for a range of T reduced temperature and reduced specific volume. So at a given value, reduced pressure value, I can just go up until actually it intersects actually with the proper line actually of reduced temperature. Then I can go here, then I can calculate the value of the compressibility factor, Z. And this chart is a chart A15 on your tables. So let's look at this chart. This is the chart. Yes, this is the chart A15. You will find this chart actually is just divided to two parts. Part A actually for value of reduced pressure from 0 up to 1. So this is chart A for reduced pressure from 0 to 1. So if I calculate the reduced pressure and its value between 0 and 1, I will be using actually chart A15A. Okay. So at this value, at any given value of reduced pressure, you will find here actually we have lines. Those lines are actually representing the values of reduced temperature. So here are the values, each of those lines representing a value of reduced temperature. Reduced temperature starting from 0.8, 0.85, 0.9, 0.95, reduced temperature 1 and 1.5, 1.1, 1.15, and so on until we reach actually a value of reduced temperature equal to 5. Okay. Then the normal lines, those lines, here normal representing actually the value of reduced specific volume, which is the volume V divided by V critical, and it is defined here. V reduced is the volume V divided by V critical, which is RT critical divided by B critical, and RT critical, B critical from table A1. Then in this case, using actually any two of those parameters, either reduce the pressure with reduced temperature, or reduce the pressure with reduced specific volume, or reduced temperature with reduced specific volume value. Then in this case, we can calculate the compressibility factor Z in this case. Okay. So let's look here. Here is the compressibility chart is given here, and actually we have here an example. Let's solve this example and see actually how we can calculate the compressibility factors. Okay. So in this example, here he said we do have determined the specific volume of refrigerant 134A. So we have refrigerant 134A. This refrigerant is at a given pressure, at pressure equal to 1 megapascal, and temperature is equal to 50 degrees C. Okay, so pressure is 1 megapascal and temperature is equal to 50 degrees C. We need to calculate in this case, we need to calculate the value of the specific volume. Okay, using first of all the ideal gas equation of state. Okay. And compare it with the actual value. The actual specific volume, which is based on the experiment, which is listed in the tables of the refrigerant. We have the refrigeration table. If you look at those tables at pressure equal to 1 megapascal and 50 degrees C, this is a shabab, we are talking about the ideal gas equation of state. So we are talking about the gas phase. So we are talking about actually the superheated refrigerant in the superheated zone. We are not talking about the subcooled or the saturation zone. We are talking about the gas phase in the superheated zone. And if you check this pressure value with this temperature, you will find actually this refrigerant in the superheated zone. Let's do this check here. For refrigerant given pressure and given temperature, so I will be going with the given pressure to table A12. This is table A13, this is 13, this is table A12. At pressure equal to 1 megapascal, so it's equal to 1000 kilopascal. So this is 1000 kilopascal. The saturation temperature is 39.3. So that means the given temperature, which is 50 degrees C, is greater than the saturation temperature. So the state is superheated refrigerant in this case. superheated refrigerant, I have to use table A13. At this pressure equal to 1 megapascal, this is the pressure table at 1 megapascal, this is the correct table, and at a temperature equal to 50 degrees C, so that should be the column. So here we can see actually this is the actual value, because this table is based on the experimental data, so this is the actual value. So V actual is equal to 0.0, this is given already in your problem, 0.021796 meter cube per kilogram. But we have this refrigerant, superheated refrigerant, at this given pressure, 1 megapascal, and given temperature, the state is superheated. We can check this actually from table, this value from table A13. Okay, this is superheated refrigerant or vapor in this case. And this is the actual value. As we said, this table is based on experiment, and this value represents the actual volume in this case. But what if I decided actually to use the ideal gas equation of state? Then in this case, we can say dV will equal to R multiplied by the temperature, multiplied by the temperature T in this case. Or we can say the ideal, the volume, the ideal specific volume, calculating the ideal gas equation of state will equal to RT divided by B. We set from table A1, this is actually a very important table for all gases, listed actually in this table. You will find the values of the gas constant R is given, molecular weight is given, critical pressure, critical temperature, and also the critical specific volume will be given in this case. So just for this working fluid, it is refrigerant 134A. We can go to table A1. Then in this case for refrigerant 134A, let's go to table A1. Here is the table for the substance R134A, which is the refrigerant. I don't know where it is. So let's look refrigerant R134A. Yes, this is a refrigerant R134A. This is actually the chemical formula of it. And then actually from this table you can get the value of the gas constant R. Here is the value, and here is the value of the critical temperature. This is the critical pressure, and also you can find the value of the critical specific volume in this case. Okay, and here are the values are given here. So find in this table the gas constant R is given in this case equal to 0.815 kilopascal. So I can get the gas constant R, I can get the value of B critical, I can get the value of T critical. Then we can substitute here, then we can calculate the ideal volume. Ideal volume will equal to R, 0.8, this is the value of R, 0.815 kilojoule per kilogram multiplied by the temperature. This temperature should be in Kelvin, so don't forget. So it is 50 plus 273.15, okay? This is the temperature divided by the pressure in this case, which is 1 megapascal. So this gas constant in this equation is calculated in kilojoule per kilogram Kelvin. So as it is kilojoule, that means this pressure should be in kilopascal in this case. And as we said, the temperature should be in Kelvin. So kilopascal from megapascal to kilopascal, 1 megapascal, which is 1000 kilopascal in this case. You can calculate this value. Then in this case, we can get the ideal specific volume in this case. And then we can compare it with the actual value and calculate the error. Using the ideal gas equation of state, what will be the error in calculating this specific volume of the gas? Then the percentage error will equal to the ratio V ideal, the difference V ideal minus V actual, and then we have to divide by V actual, not dividing by V ideal. In this case, we calculate the error in reference to the actual value, not the ideal value. So it is V ideal minus V actual divided by V actual multiplied by 100. V ideal, which is the value we should have calculated here, and this is the value of V actual. V ideal, if you calculate this value, V ideal will equal to In this case, 0.26325 or 0.02635 minus the actual value, which is this value of can just check this 21796 divided by the actual 0.0219796. Multiply this equation by 100. If you calculate the percentage error in this case, you'll find this error actually is around 20%, or actually it is 20.8%. So if I decided case B to use the compressibility chart using the parameter Z, in this case actually instead of using BV is equal to RT, it will be just BV equal to ZRT. So using the ideal gas equation of state, the error in calculating the volume was equal to around 21%. But in this case, if I use the compressibility chart instead of the ideal gas equation, BV is equal to ZRT, I have to calculate the parameter Z in this case. Given the pressure is equal to 1 megapascal, the temperature is equal to 50 degrees C in this case. So I will be calculating the reduced pressure, which is the ratio between B divided by B critical. Pressure in this case is 1 megapascal. The critical pressure, which is the value we can get actually from table A1, critical pressure is 4.059 megapascal. So if this one is megapascal, that one also should be megapascal. If you calculate the reduced pressure value, it will be equal to this value, which is 0.246. Also, given the temperature, I will be calculating the reduced temperature, which is T divided by T critical. Temperature is 50 degrees C, so 50 plus 273.15 divided by the critical temperature, which is the value from table A1 for refrigerant 134.8 is equal to 374.2. If you calculate this value, you will find the reduced temperature is equal to 0.84. But if we've given here pressure plus the specific volume, then in this case I will be calculating the reduced pressure and calculating the reduced specific volume, which is the ratio between the specific volume divided V divided by V critical, and the V critical is equal to RT critical divided by B critical. B critical and T critical and the value of R, all of these properties are given actually in table A1 for different gases in this case. So to calculate the parameter Z, we have to have actually two reduced value, either reduce the pressure with reduced temperature or reduce the pressure with reduced specific volume. Any two reduced value, then I can go to chart A15. Then we can calculate the value of the parameter Z. In this case, given pressure and temperature, then I will be calculating reduced pressure and reduced temperature using the value of the critical values actually given in table A1. So if you calculate the reduced pressure, it will equal to 0.24 and reduced temperature is about 0.8. Then I will be going to chart A15. The reduced pressure value is less than 1.24. Then I will be using chart A, which is actually for a reduced pressure from 0 up to 1. Here the value is 0.24. This is 0.2. This is 0.3. 0.24. It will be something in between here. And the value of reduced temperature is 0.86. This is the value of reduced temperature 0.8. This is 0.85. This is 0.9. That means actually at reduced temperature 0.86, it will be just a line in between 0.85 and 0.9. So here we'll just draw a line at pressure, reduce the pressure equal to 0.24. Till it intersect actually with the proper temperature line. It should be something a point here around this point, so we can go here and we can read the value of the reduced temperature, the value actually of the compressibility factor Z. In this case, the value of the compressibility factor Z, based on the reduced pressure and reduced temperature from chart A15, will equal to 0.84. It is not any exact value, just when you go to the table, if you got the value 0.81, 0.82, 0.83, so it doesn't matter because it depends on actually your vision. So in this case, actually, this is the parameter Z. So I have to calculate the specific volume based on actually the compressibility chart. And in this case, the volume in this case, based on this equation, will equal to ZRT divided by V. So the specific volume will equal to ZRT divided by V. RT divided by V, which is V ideal. We have just calculated actually from step number A, which we have calculated this value 0.026. This is the value 325 meter cube per kilogram. So if we multiply this by the parameter Z, which we have calculated 0.84, then we can calculate the specific volume based on the compressibility chart. It will equal to 0.0222116. This is meter cube per kilogram. If you calculate actually with the actual value and calculate the percentage area in this case, which is the actual value from the table, minus the value calculated using the compressibility chart, divided by the actual value and multiplied by 100. In this case, you will find actually this error is only about 2%. So the error has dropped from the ideal gas equation of state from 21%. It has dropped down actually to about 2% only when we use the modified equation using the compressibility chart or using the compressibility factor Z in this case, which you can actually modify for the actual value of the specific volume in this case. Type in your exam, what we are going to do is what? In your exam, I will be assuming actually any problem, any gas is an ideal gas. BV is equal to, just BV equal to RT. Unless he asked you directly to use the modified equation, which is BV is equal to ZRT. And in this case, I will be calculating the compressibility factor Z in this case. So in any problem, I will be assuming the gas as an ideal gas, and I will apply this equation BV directly equal to RT, unless he asked it actually to calculate the compressibility factor Z. But if in your exam, if I said I have a gas at a given pressure and a given temperature, let's say, and he asked you about actually the status of this gas, is it ideal gas or real gas? Then in this case, I will be calculating the parameter Z. If it is equal to 1, if this is equal to 1, then actually it is an ideal gas. And this is very rare case to calculate Z to be 1. So if he asked you about the status of the gas, in this case, most probably it is a real gas because the value of Z should be greater than or less than 1. So that means actually the case is real gas. So anyway, I will be calculating Z in this case, and I will be using this equation throughout the problem. BV is equal to ZRT, and I have to calculate Z using a chart, actually chart A15 in this case. Okay. Type like the refrigerant, shabab, here I have to just reflect here. This is actually the saturation curve for water for steam. For steam at very low pressure, low density, and even high temperature or low temperature, it doesn't matter. If it's at low pressure, steam, let's say steam at 10 kilopascal or 100 kilopascal even, if you calculate in this case the error in calculating a specific volume, like what we have done here, you will find this error is almost zero in the superheated zone. So for steam at low pressure in the superheated zone, we can apply the ideal gas equation of state to calculate the actual volume of the gas without actually any error in this case. The value of the error is equal to 0. But when we are actually close to the critical pressure, as the pressure gets higher, then in this case the value of the error in calculating the volume gets high. You can see here, close to the critical pressure, actually here the error is equal to 271 something. So the error gets very high actually in calculating the specific volume if the pressure actually is close to the critical value in this case. Okay. So this is actually all what I want to just press on regarding actually the compressibility chart. Inshallah, next time we'll see some other modification for the ideal gas equation of state based on the empirical correlations. Okay, thank you.